Let's examine the requirements for bonding around concentric knockouts on enclosures, especially where the voltage to ground exceeds 250 volts. We'll consider two examples to clarify when bonding bushings are necessary. In the first example, we have an electrical metallic tubing or IMT branch circuit conduit running from a punched knockout in a panel board to a junction box with a concentric knockout. Inside the conduit, there's an equipment grounding conductor or EG that terminates at the panel and connects to the junction box. In this scenario, a bonding bushing is not required at the junction box. This is because the conduit is already bonded at one end by the connector installed in a punch knockout at the panel. Additionally, the junction box is bonded by the equipment grounding conductor connected at both ends. Now let's move on to the second example. Here, the setup is similar to the first, but the conduit has concentric knockouts at both ends, and there's an equipment grounding conductor inside the EMT. In this case, bonding bushings are required at both ends of the conduit. The requirement in National Electrical Code, or NEC, section 314.20 applies when the voltage to ground exceeds 250 volts, which is the condition we are considering. Bonding bushings are essential to ensure a continuous, low-impedance bonding path between the enclosure, which is the junction box, and the raceway, which is the conduit. The reason for this is that the concentric knockouts at both ends of the conduit create separate grounding paths for the enclosure and the raceway. Without bonding bushings, these paths would not be properly connected, potentially creating a shock hazard. Therefore, it's crucial to install bonding bushings at both ends of the conduit to bond the junction box and the conduit to the grounding system. In summary, the first example does not require a bonding bushing at the junction box because the conduit is bonded at one end and the junction box is bonded by the equipment grounding conductor. However, the second example requires bonding bushings at both ends of the conduit due to the concentric knockouts at both ends, which necessitate a continuous, low-impedance bonding path between the enclosure and the raceway when the voltage to ground exceeds 250 volts. It's important to remember that NEC section 314.20 is the governing requirement in this scenario. This section stipulates that where circuit conductors are run in a metal raceway or metal cable assembly that enters the enclosure through a concentric or eccentric knockout or similar opening, bonding jumpers shall be used to ensure electrical continuity between the raceway or cable assembly and the enclosure. The size of the bonding jumper shall be based on the size of the circuit conductors as outlined in NEC Table 250.102. The bonding jumper shall be long enough to permit removal of the equipment without damage to the bonding jumper or the connections. The location of the bonding jumper shall be accessible for inspection and maintenance. The bonding jumper shall be installed in accordance with NEC 250.64. which covers the installation of bonding jumpers and their protection. The bonding jumper shall be connected to the equipment grounding bus or terminal within the enclosure. When using bonding bushings, they must be properly installed and tightened to ensure a reliable electrical connection. The bonding bushing should be listed and labeled for the purpose. Additionally, the bonding jumper should be securely connected to the bushing and the enclosure. It is crucial to inspect bonding connections periodically to ensure they remain tight and free from corrosion. Loose or corroded connections can compromise the effectiveness of the bonding system. Consider using anti-corrosion compounds on bonding connections to prevent corrosion, especially in damp or corrosive environments. Always refer to the latest edition of the NEC and local codes for specific requirements and interpretations. Electrical codes can vary by jurisdiction, so it's essential to comply with the applicable regulations in your area. Consulting with a qualified electrical inspector or engineer can help ensure compliance with the code and proper installation practices. Also be aware that other sections of the National Electrical Code, or NEC, can be related to the requirement to bond around concentric knockouts on enclosures where the voltage to ground exceeds 250 volts. These sections provide additional guidance and requirements related to grounding and bonding. Firstly, NEC 250.4, which covers general requirements for grounding and bonding. It provides fundamental principles for establishing effective ground fault current paths and minimizing voltage differences between conductive parts. Secondly, NEC 250.8, which covers connection of grounding and bonding equipment. It specifies methods for connecting grounding and bonding conductors to equipment, enclosures, and other conductive parts. Thirdly, NEC 250.92, which covers bonding of metal enclosures containing service conductors. It requires bonding of metal enclosures containing service conductors to ensure electrical continuity and prevent voltage differences. Fourthly, NEC 250.96, which covers bonding of metal enclosures and raceways. It requires bonding of metal enclosures and raceways containing other than service conductors to provide a low impedance ground fault current path. Fifthly, NEC 250.97, which covers methods of bonding at service equipment. It specifies methods for bonding metal enclosures and raceways at service equipment, including the use of bonding bushings, wedges, or other approved devices. Sixthly, NEC 300.3, which covers conductors of different systems. It requires conductors of different systems to be separated and identified, which can impact grounding and bonding requirements. Seventhly, NEC 314.4, which covers metal boxes. It provides requirements for the installation and support of metal boxes, including provisions for grounding and bonding. Eighthly, NEC 314.40, which covers boxes, canopies, and fittings. It provides requirements for the installation and support of boxes, canopies, and fittings, including provisions for grounding and bonding. Ninthly, NEC 408.41, which covers ground bus. It requires switchboards and panel boards to have a ground bus for connecting equipment grounding, conductors, and bonding jumpers. Tenthly, NEC 408.42, which covers neutral bus. It requires switchboards and panel boards to have a neutral bus for connecting neutral conductors. 11thly, NEC 250.102, which covers bonding jumpers and connection. It provides requirements for the size and installation of bonding jumpers, including those used to bond metal enclosures and raceways. 12thly, NEC 250.104, which covers bonding of piping systems and exposed structural steel. It requires bonding of metal water piping systems, metal gas piping systems, and exposed structural steel to the grounding electrode system. 13thly, NEC 250.122, which covers size of equipment grounding conductors. It specifies the minimum size of equipment grounding conductors based on the overcurrent protective device rating. The interaction and application of these sections will depend on the specific details of the electrical installation. However, understanding these related sections can help ensure a comprehensive approach to grounding and bonding. Let's delve a bit deeper into the specific requirements outlined in NEC 314.20. This section primarily addresses the need for bonding when dealing with metal enclosures and raceways that house electrical conductors. As we've established, when the voltage to ground exceeds 250 volts, the code mandates that you establish a continuous, low-impedance ground fault current path. This is especially critical when enclosures are connected to raceways through concentric or eccentric knockouts. The reason concentric and eccentric knockouts pose a challenge is that they can introduce impedance into the grounding path. The multiple layers of metal and the sometimes less than perfect contact between them can impede the flow of fault current. This increased impedance can slow down the response time of overcurrent protection devices, such as circuit breakers or fuses, in the event of a ground fault. To counteract this, bonding bushings are used to create a more direct and reliable connection between the enclosure and the raceway. These bushings are designed to provide a low impedance path for fault current to flow back to the source, allowing the overcurrent protection device to trip quickly and clear the fault. The installation of bonding bushings typically involves removing any paint or coatings from the contact surfaces to ensure a good electrical connection. The bushing is then securely fastened to the enclosure and the raceway, often with a locknut or other suitable hardware. A bonding jumper, which is a conductor used to connect the bushing to the grounding system, is then attached to the bushing and to a designated grounding point, such as the equipment grounding bus or terminal. It's worth noting that the size of the bonding jumper is determined by NEC Table 250.102, which is based on the size of the circuit conductors. The larger the circuit conductors, the larger the bonding jumper required. In addition to bonding bushings, other methods can be used to achieve the required bonding, such as bonding wedges or other listed devices. However, regardless of the method used, the goal remains the same: to create a continuous, low-impedance ground fault current path. When dealing with existing installations, it's important to inspect the bonding connections periodically to ensure they remain tight and free from corrosion. Over time, connections can loosen and corrosion can develop, both of which can compromise the effectiveness of the bonding system. If any issues are found, the connections should be cleaned and tightened, or the bonding hardware should be replaced as needed. Furthermore, it's important to consider the environment in which the electrical system is installed. In damp or corrosive environments, the risk of corrosion is increased, and it may be necessary to take additional measures to protect the bonding connections, such as applying anti-corrosion compounds. Another important aspect to consider is the type of raceway being used. While we've primarily discussed EMT in the context of these examples, the bonding requirements also apply to other types of metal raceways, such as rigid metal conduit, or RMC, and intermediate metal conduit, or IMC. The specific installation methods may vary depending on the type of raceway, but the underlying principle of establishing a continuous, low-impedance ground fault current path remains the same. In summary, when dealing with concentric or eccentric knockouts on enclosures where the voltage to ground exceeds 250 volts, it's crucial to understand and comply with the bonding requirements outlined in NEC 314.20. By using bonding bushings or other approved methods, you can ensure a safe and reliable electrical system that protects against shock hazards and minimizes the risk of damage in the event of a ground fault. In addition to the scenarios we've discussed, it's worth considering a few other common situations where bonding is required. For example, when installing electrical equipment outdoors, such as air conditioning units or swimming pool pumps, it's important to bond the equipment to the grounding electrode system. This helps to prevent voltage differences between the equipment and the surrounding earth, which can create a shock hazard. Similarly, when installing electrical equipment in hazardous locations, such as gasoline dispensing facilities or chemical plants, it's essential to bond all metal enclosures and raceways to the grounding electrode system. This helps to prevent the accumulation of static electricity, which can ignite flammable vapors or gases. In these situations, the bonding requirements are often more stringent than those for general-purpose electrical installations. It's important to consult the applicable codes and standards for specific requirements. Moreover, it's worth emphasizing the importance of proper grounding and bonding throughout the entire electrical system. A well-designed and properly installed grounding and bonding system is essential for ensuring the safety and reliability of the electrical system. It provides a path for fault current to flow back to the source, allowing overcurrent protection devices to trip quickly and clear the fault. It also helps to minimize voltage differences between conductive parts, reducing the risk of electric shock. In addition to complying with the NEC and other applicable codes and standards, it's important to follow best practices for grounding and bonding. This includes using high-quality grounding and bonding hardware, ensuring that all connections are clean and tight, and periodically inspecting the grounding and bonding system to ensure it remains in good condition. By following these guidelines, you can help to ensure a safe and reliable electrical system that protects against electrical hazards. Furthermore, consider the impact of harmonics on grounding and bonding systems. Harmonics are distortions in the electrical waveform that can cause increased current flow in grounding conductors. In systems with significant harmonic content, it may be necessary to increase the size of the grounding conductors to accommodate the increased current. Additionally, it's important to ensure that the grounding and bonding system is properly designed to minimize the effects of harmonics, such as installing harmonic filters or using shielded cables. It's also worth noting that grounding and bonding requirements can vary depending on the type of electrical system. For example, the grounding and bonding requirements for a separately derived system, such as a generator or transformer, are different from those for a utility-supplied system. In a separately derived system, the neutral conductor is typically bonded to ground at the source of the system. This creates a reference point for the system voltage and helps to prevent voltage differences between the neutral conductor and ground. In a utility-supplied system, the neutral conductor is typically bonded to ground at the service entrance. However, in some cases, it may be necessary to provide additional grounding electrodes to supplement the service entrance ground. The specific grounding and bonding requirements for a particular electrical system will depend on a variety of factors, including the type of system, the voltage level, and the location of the system. It's important to consult the applicable codes and standards for specific requirements. When performing electrical work, it's important to follow safe work practices to prevent electrical shock and other hazards. This includes de-energizing circuits before working on them, using appropriate personal protective equipment such as gloves and safety glasses, and following lockout/tag-up procedures to prevent accidental re-energization. It's also important to be aware of the potential hazards associated with working near energized equipment such as arc flash and arc blast. Arc flash is a dangerous electrical explosion that could occur when a short circuit or other fault occurs in an electrical system. Arc blast is a powerful pressure wave that can be generated by an arc flash. Both arc flash and arc blast can cause serious injuries or even death. To protect against these hazards, it's important to follow safe work practices and use appropriate personal protective equipment. For example, when working near energized equipment, it may be necessary to wear arc-rated clothing and a face shield. It's also important to be trained in arc flash safety and to understand the potential hazards associated with working near energized equipment. Additionally, consider the impact of surge protection on grounding and bonding systems. Surge protective devices, or SPDs, are used to protect electrical equipment from voltage surges caused by lightning strikes, power line disturbances, and other events. SPD typically divert surge current to ground, which can place additional stress on the grounding and bonding system. To ensure that the grounding and bonding system can handle the surge current, it's important to properly size the grounding conductors and bonding jumpers. Additionally, it's important to install SPD in accordance with the manufacturer's instructions and to follow any applicable codes and standards. In summary, the grounding and bonding system is a critical component of any electrical system. It provides a path for fault current to flow back to the source, allowing overcurrent protection devices to trip quickly and clear the fault. It also helps to minimize voltage differences between conductive parts, reducing the risk of electric shock. By following the guidelines and recommendations outlined in this discussion, you can help to ensure a safe and reliable electrical system that protects against electrical hazards.